Knowledge, or the AOK program, over the last 4 or 5 years. The AOK program is, of course, a hosted program under the CSIR. But yeah, this recap is all about the AOK project. I gave a presentation at the Cyber conference about a year ago on a similar topic, but that presentation was only on the past year or two. So I'll be taking a step back today and giving sort of a bigger overview of the research that was done from the start of the program, but with a focus on a couple of specific technologies. So the topics that I'll cover today, I'll give some background about the AOK program, the intent, the approach of the program. Then I'll explain a bit why I will be focusing on GPR and ERT, those two technologies. I will explain why not GPR and ERT. You will understand when I get to the slide what I mean by that. I'll list a few research topics for each of those technologies. I'll, of course, include quite a few case studies for GPR and ERT. Then a bit later in the presentation, I'll bring in the LiDAR technology as well, and I'll talk about the value add that LiDAR offers to in-mine geophysics in general, but specifically to those two technologies. I'll talk a bit about the application guidelines that we produced about a year ago. And also a slide or so on the way forward and possible new research topic related to these topics. So let's start with the AOK program. I'll maybe jump right into the objectives. So the AOK program, the idea behind it is to basically address the following three questions. Where is the reef ahead of the mining phase? What is the grade and what is impeding extraction? Obviously referring to geological disruptions and structures. The two main drivers is essentially optimal extraction and obviously contributing to the zero harm objective. Now, maybe just a few pictures to illustrate those ideas. So the little schematic you see on the left of this slide is your typical deep level conventional mining layout in an ideal world. So the yellow plane would represent your planar ore body or your tabular ore body. It could be the Merensky, it could be the BCR, it could be the UG2. And then that ore body is accessed at depth using a sequence or series of excavations and tunnels, your vertical shaft, your ridges, your crosscuts, to get to a little block on that horizon that will then be mined out sequentially. The final excavations that provide access are your raised tunnels that are in the same plane as the reef. Now, unfortunately, your tabular ore bodies don't behave like in that schematic. They often misbehave. And the pictures on the right show typical examples. On gold, you often find that your reef horizon has undulations or topography on it. A number of slopes or terraces might deviate or cause a deviation from your flat-lying horizontal planar reef. In platinum, you get potholes or slump structures, and there's just simple schematic there at the bottom showing different types of potholes. There's a few more types, but essentially you can get that your reef is slumped locally or completely eroded away in a sense in a localized area. The schematic to the far right is an actual mine plan that shows that these potholes and other intrusions can often affect a 2B mine block quite severely and impact on the mineable or the payable ground. Safety is obviously a big thing, the zero harm objective. Now, often those structures that I showed in the previous slide, your potholes, your faults, whatever, they are associated with poor ground conditions most often. And we know that falls of ground consistently contribute quite significantly to mining fatalities in South Africa. I've got two pie charts here, one from 2020 that shows in that year almost half of all fatalities were related to falls of ground. And the one from last or 2 years ago almost 40% or 30% foreground. And that picture doesn't really change much from year to year. And we feel that the geophysical technologies like the ones that I'll be talking about can actually contribute to giving us advanced warning of these structures and hazards. So this talks about the zero harm objective, and then just maybe one little picture that talks about the optimal extraction. And this one is often difficult to convey, but we, in one of the AOK projects, look at the actual value locked up in a to-be mined block. And just for the calculation, we assumed a medium-sized block of about 120 by 120 meters, an ore body of about 1 meter thickness, and a grade of about 6 grams per ton. We looked at the platinum price at the time, and the calculation shows that a little block like that has a value of about 150 million South African rands. Now you can just imagine if a quarter or a third or a half of that block is impacted by geological structures that you're not aware of when you start mining out that block. It's obviously huge losses, and it just messes up your whole planning. So in the AOK project, going back a few years, when we started out, this is just a roadmap. I'm not going to talk about this slide in detail, but basically the idea was to start almost with a shotgun approach. Look at any possible geophysical technology or related technology that could provide answers or useful outputs for those two drivers of optimal extraction and zero harm. And then to look at, obviously, at the user requirements, the problems that the mines encounter, and then start testing some of those promising technologies and essentially whittle them down to a handful of let's call it most promising technologies. And the thinking was to ultimately get to a point where we can get the mines to embrace and adopt and implement some of these technologies to allow them to see these hazardous structures or disruptive structures ahead of mining. And basically to enable, as people often refer to it, as glass rock mining. So this is another picture. I apologize for the quality. It's quite a lot of text there, but basically this just shows that initially we considered quite a wide range, more than a couple of dozen of different technologies, and we looked at also quite a range of typical mining problems encountered at deep level, and we tried to match some of these technologies to those problems and see where the best fits were and which technologies needed further research and development. This is just basically a further nutshell summary of some of the top problem scenarios that we encounter in in-mine geophysics, ranging from looking into the hanging wall for beam thickness, dome structures, tracking the reef ahead of mining, looking at the reef continuity, cross-cutting structures, of course, faults and dikes, for example, and then even problems like lost raised bores or ore passes or drain holes that because of deviations in the drilling couldn't be found. Fracture characterization or monitoring of preconditioning, that's also quite a big thing. And what you can see from this table is that techniques like GPR, ground penetrating radar, and bore radar feature quite heavily in the applicability discussion. Also, ERT is one that features specifically on mapping the reef continuity and geological structures ahead of mining. But the main reason why we focus on GPR ERTs is maybe a bit because of an internal bias. We at the CSIR focus quite heavily on the GPR, ERT, and bore radar technologies. I'm not going to include, or I deliberately excluded, bore radar from this presentation today, simply because it wasn't really a focus of R&D in the AOK program. But this little schematic just summarizes how we envisage the mines of the future to actually exploit these technologies. If you could look at your typical mining environment, your mining or your to-be mined blocks, and you could do some sort of reconnaissance mapping using a technology like ERT, by reconnaissance, I mean a technology that maybe gives you a resolution of a few meters, plus minus 5 meters. That could then help you to identify disruptive or hazardous structures ahead of mining, the gross features, if you like. Then you could obviously move in with something that's a bit higher resolution, like your bore radar, and you could get you can characterize your problem or your anomalies in a bit more detail, maybe going down to a resolution of maybe 3 meters. GPR is quite a nice technology because it's applicable to almost any stage of mining, whether you are in the stoke or in the haulage. You can always use GPR to look at the condition of the hanging wall or the sidewalls. And then in more recent times, topics like data analytics and artificial intelligence has obviously come into play quite a bit. And the way we see the mines of the future operating is to take almost a holistic or integrated approach to these technologies and use them to produce either virtual 3D models of the ore body environment or safety risk maps, maybe, and all of those things can contribute to decision support by the rock engineers, the geologists, the mine planners. Okay, so moving on to the technologies themselves, I'll first talk a bit about GPR. I'm not going to go into heavy technical detail. I think most of you in this call probably know what GPR is all about. But essentially, you have a transmitter and a receive antenna. You transmit radio energy into the ground, and you use a receiver to measure reflections that come off any discontinuities. It's basically your dielectric discontinuities in the subsurface. And things like layer boundaries, localized anomalies, they all often show up as radar anomalies on your radar outputs. This is just to show what you typically see in radargrams. The slide or the picture at the top is just is not real data. It's modeling results, just showing you the two typical features that you see in most radargrams. You either use it to track a horizontal or near horizontal horizon, or you see those typical hyperbolic reflections that are associated with localized dielectric anomalies. The one at the bottom is an actual radargram, and you can see that apart from your hyperbolic reflections and your horizontal features, you can also expect quite a bit of noise in a lot of your GPR results. There's different types of noise, ringing, for example. And one of the ideas behind processing, GPR processing, is to actually suppress those noise, unwanted noise responses, and to emphasize the features of interest in the radargram. Just for some historic context, I thought this would be interesting. These are some of the very first GPR results from the South African mining industry. Many years ago, I think it was late 80s, the CSR or was then still Mining Tech and Comro introduced the technology of GPR to the local mining industry. And in fact, that picture at the top left is the very first underground GPR survey that was done. And I'm not going to talk about the detail of these surveys, but these are all from those first 4 or 5 years of GPR research. And those that are familiar with GPR will immediately recognize that maybe 20, 30 years ago, the technology wasn't as advanced as it is today, and your performance of your GPR was maybe a bit iffy. Just to show you the contrast, these are more recent GPR results. This is already almost 20 years old. These come from the former Platmine Research Collaborative Program. And you can see GPR can, in ideal conditions or in good conditions, can be used to track chromatite stringers, things like the triplets or the leader seam, and it can also be used to identify hazardous structures like your domes, your curved joints, and so on. This is just an example of a more detailed or a radargram bit of detail where you can see different types of features in the same radargram. And most often your correlation between your radar responses and your lithology or your expected lithology is quite good. I just want to say a few words about, because this becomes relevant a bit later in the presentation, about one of the concepts in GPR that we call the range resolution trade-off. So you get different frequency antennas if you operate in the frequency domain like most GPR systems do. If you want to see as far as possible into the rock, you need to go to a low frequency, something like 100 megahertz or maybe 50. And then you can get a range in typical conditions of up to 8 or 10 meters into the rock. But then your resolution will only be about maybe 15, 20 centimeters. If you want to improve your resolution to maybe a few centimeters, you need to go to the really high frequencies, but then you compromise your range. So, for example, the one that you use most often underground is the 500, the one there in the middle. We typically get 4, 5, 6 meters range at the resolution of about 5 to 10 centimeters, and that's quite a good middle ground for in-mine, especially for the hanging wall studies that we do with the GPR. So these are typical GPR applications in the underground environment. As I mentioned before, immediate hanging wall studies, looking at beam thickness and dome structures. You can also use it for tracking the topography ahead of mining if the excavation geometry allows it. You can look for cross-cutting structures. And I also mentioned the lost raised bores or ore passes previously, and the fracture monitoring, and also monitoring of preconditioning. Now, I mentioned earlier that GPR was first used in the local mining industry as long ago as late 80s or early 90s. But there's always been a bit of a, how can I put it, a bit of a resistance to actually embracing and implementing the technology. In the first, let's call it decade or so, the main complaint, the equipment was bulky and cumbersome to use, which was quite a valid summary, if you like. During the plat mine era, there were still complaints that the equipment was bulky and that it lacked real-time data displayed because you couldn't really see as you were acquiring data what you were looking at. But there was possibly a wrong focus at the time. I'll say a bit more about that shortly. And then more recently, when we started with the AOK program, the main complaints were 3D visualization. It was sort of at the time when 3D visualization of various geophysical methods or technologies became quite a hot topic. And up to that point, most people were still looking at 2D GPR results. Georeferencing has always been a bit of a problem for in-mine geophysics because of the lack of GPS. And then integration is a big thing. We often provided outputs of geophysical results to clients in a local coordinate system, with reference to specific features or infrastructure in the mining space where we operated. And it has always been quite a challenge to georeference your data and to integrate it with mine CAD software, mine planning software, and so on. So just maybe some reasons why there might have always been a limited interest. I mean, it's getting better. A lot of people are using GPR and have bought systems. But there's often an inappropriate use of GPR. It gets used in areas where it doesn't work really well, like mesh-supported excavations, or people use sub-optimum survey parameters. So it basically boils down to the problem of needing an expert, or at least somebody with experience in GPR to be able to execute the surveys and to interpret and understand the data. And a lot of the mines these days don't have in-house geophysicists anymore. So it's often a challenge if they buy their own systems and they're not quite sure how to use it. So that speaks to a lack of training and skills in terms of processing, interpretation, but also, as I said, data acquisition. And then again, the big thing is if you can't integrate the data with your mine planning software or your CAD, your software, it's a bit of a problem. So when the AOK project started looking at GPR in a bit more detail, these are the key research topics that we focused on. The 2D versus 3D issue, and trying to generate 3D models of the rock mass, not just radar graphs. Georeferencing, obviously, big thing. And then we spent quite a bit of time more recently on integrating our outputs with CAD software and other visualization software. Training for mine personnel, that's an important aspect of recent AOK efforts. And then things that we also highlighted as key research topic is the introduction of AI and machine learning. And then ultimately, you want to remove your operator from the unsafe spaces. So we considered the mounting of GPR sensors on mobile mining machines or robotic platforms. Okay, moving on to ERT. So ERT stands for electrical resistance tomography. It's essentially a geoscience equivalent of the well-known medical imaging technology. There's a lot of technical detail in this slide, but basically what you do is you have an area that you target and you place electrodes, galvanic electrodes around your area of interest. You don't have to surround it completely. You can often only gain access from two sides, like if you have two coplanar borers drilled from a development, or as we often apply it, we use two coplanar tunnels to do tunnel-to-tunnel tomography. And the idea is to probe for anomalies or changes in your resistivity structure in the plane that you are defining with your electrode setup. And if I can just move to the next slide, this is not schematic, it's not real data. But what we then typically do in the conventional mining layout is, or mechanized sections, we try to put electrodes around, or at least on two sides of that to be mine block, and then do our resistivity surveys and produce some sort of a resistivity map that shows us where the anomalous features are. And those changes or anomalies in your resistivity structure is often associated with structures like potholes, intrusions, and faults. Here's some example. This comes from the flat mine era still. These are examples of actual in-mine ERT surveys. So these were done in areas where we knew there were potholes and IRUPs present. The one on the right, for example, was a stope that was abandoned because of all those potholes. And we did surveys in the available excavations around those areas, and were able to show that ERT can definitely be used to map potholes and IRUPs where it does disrupt continuity of the reef horizon. So maybe not as many applications or problems that you can solve as with GPR, but ERT is good for constant mapping of to-be mined blocks, delineation of major disruptions to the reef continuity, specifically potholes, intrusions like your IRUPs and faults. Now, in terms of why people didn't really want to adopt or embrace ERT, it's always had challenging logistics. It's not like your GPR where you can carry your system in a backpack. It involves quite a lot of cabling and electrodes. And especially in your production environments, that presents a problem, because just setting up your whole server area takes a few hours, and it's often not possible to have that type of access to mining sites. It does require specialist involvement and oversight. The value add, I think, until fairly recently, until the work we did under AOK, was probably not fully realized or appreciated. And when we first researched ERT in the Platmine Collaborative, the bore radar technology at the time emerged, and a lot of focus was put on that technology. And ERT was almost left by the wayside in a sense. So also for ERT, we identified at the start of the AOK project a number of key research topics. You can see them there. I'm not going to read through all of them, but focusing a lot on the logistical side of things, and then also things like georeferencing and training of personnel that we feel is quite important. As part of the project or the AOK project, I think last year or 2 years ago, we actually looked at the whole ERT survey procedure from selecting a site and survey design right through to doing the modeling and the interpretation and getting the output and georeferencing that. And we identified a number of red flags and where we needed to improve the whole process. And a lot of these flags actually related to the whole logistics of data acquisition and georeferencing. I'm not going to go into a lot of detail, but just to show you what we achieved, we made some changes. Also, some of the technologies improved since the Black Mine days. For example, something simple like your portable drilling technology, using lithium batteries instead of the battery technology that was around 20 years ago, allowed us to cut the survey preparation time quite significantly. Also, data acquisition is now a lot faster due to the modern multi-channel automatic resistivity systems that are available. And you can see there at the bottom the totals. A typical in-mine ERT survey took anything from 4 to 8 hours back in the day. And we showed that it's now quite possible to do an ERT survey, including site preparation, inside a single shift of maybe 4 hours or so. Okay, let's look at some case studies. Now going to go back to GPR first. So these are just a collection of pictures to show you what GPR can do for you. This is an example of identifying lithological units. This is from Tupong mine in the Free State, looking at the change over from the basal quartzite to the khaki shale and the leader quartzite. You can also see some faults appearing on that radargram. You can also use GPR if the geometry, the excavation geometry allows it to track your reef continuity. This is an example of looking at the Merensky reef continuity from a decline footwall. Fracture characterization in the hanging wall, that's probably the most common or one of the most common GPR applications. You can look for your typical horizontal fracturing, your dipping fractures, and this is obviously very useful information for your rock engineers. These are examples. It's not often very doesn't provide good results always, but you can also look ahead of the face at face parallel stress induced fracturing. This is just an example of that. And then moving on to the 2D versus 3D survey issue. So many years ago, it was very difficult to do 3D surveys simply because the computing power wasn't up to scratch to be able to produce 3D GPR models. So the idea behind the 3D or grid GPR survey is instead of just doing a few selected 2D lines, you acquire data over a grid using parallel lines for a constant line spacing. You can also do those lines in 2 perpendicular directions if you have time and you want a bit more resolution or more detail. And then these are the type of outputs that you can expect. This is just showing some mythology in the immediate hanging wall, looking at it from different perspectives. You can look at your different sections there on the left, or you can look at the whole cube of 3D GPR data on the right. Yes, I think in the next couple of slides I'll be showing a few of these 3D examples. This is looking at the top and bottom contexts of a chromatite package. And at the bottom, you can see there, if you have a nice visualization software, you can take your radargram outputs or your 3D data cube and you can display it in something like your I think this was done in Boxler, where you can look at the different horizons from a 3D perspective. You can also use or make use of depth slicing. Then in the middle, you see two radograms where we were looking at the chromatite package in one of those previous examples. And by looking at different depth slices, you can see the response, how the response differs for intact rock versus the chromatite package and the fractured zone beyond that. And you can see the two depth slices to the left and far right of those radograms. You can also use it to map shear zones. I think this was done at, if I remember correctly, Eland Mine, where you can see the top, again, the top and bottom contact of the shear zone, and that's quite prominent in the hanging wall at that mine. And this is maybe a good example of why the 3D approach is actually quite useful. If you just look at individual 2D lines, you cannot infer that curved nature of that shear zone. You can see that the shear zone has a almost curve with respect to the hanging wall surface. And that type of information is often useful to the rock engineers for support design and similar purposes. This is maybe not the best radograms, but you can pick up two discontinuities. Then this is your typical parting plane beam thickness scenario, which GPR does really well. I mentioned earlier that sometimes GPR is used in the wrong places. This is a typical example of GPR being used in a mesh environment. Now, some of you will already know that it's not impossible to do GPR where there's mesh or roof bolts. Roof bolts is less of a problem, but it all depends on the frequency that you're using and also the spacing between the roof bolts and the spacing of the mesh. So sometimes you do get through, but more often than not, you see these horrible signal reverberations and ringing in your GPR data that often masks any signals from useful geological reflections deeper in a section. Okay, I mentioned in the beginning that I will just introduce or talk a bit about LiDAR. Not so much about the LiDAR technology itself, but more about the value add that LiDAR offers. So a few years ago, we started playing around with LiDAR. On the left, you can see one of those tripod-based LiDAR systems, the terrestrial LiDARs. More recently, we started experimenting with the portable SLAM technology, like your GeoSLAM, Zebra Horizon sensors. There are very similar other LiDAR sensors out there as well. We played around with the GeoSLAM. And we use the LiDAR for georeferencing purposes. And we first demonstrated this actually not using the GeoSLAM data, but the terrestrial data. The MMP test mine at Masebe actually has a mine plan associated with it that's based on a very crude LiDAR point cloud. You can see the point cloud there on the bottom left. And we actually use that point cloud to georeference our one ERT survey that was done at Masebe around that Michel's pillar. And we ultimately were able to take the ERT output and overlay it on the mine plan in its proper spatial position based on the LiDAR point cloud position. Now, LiDAR also has other useful potential features. If you have a really high quality you can look at the fracture characteristic of that animal surface, and you can often pick up small scale fractures that is not necessarily visible to the naked eye when you're underground in the excavation. And this is quite useful because if you have a GPR section of the same hanging wall area, you could tie in some of these anomalies in your LiDAR fracture map with the fractures that you observe in your GPR sections or 3D model. With the advent of the more modern SLAM technologies, we were quite impressed with the type of results that you can get by just walking around with that sensor in a few minutes, without using a tripod, you can get these type of images out, very high resolution images of your excavations. You can see there Borden pillar working on the left, and Michelle's pillar at the bottom. You can really see a lot of detail in the surrounding rock faces. The other useful thing with the LiDAR data is you can actually use it for creating thin layers or surfaces of your hanging wall surface. And this is an example from the survey again, where we took the hanging wall or the point cloud of the excavation. It's actually the point cloud that I showed you in the previous one. This one at the bottom. We took that point cloud and extracted only the hanging wall portion where we did the GPR survey, and then created a thin layer and a surface from that. Now, why is this important? Often, well, if you work in maybe a mechanized section, your hanging wall surface will often be quite flat and smooth, but that's not always the case, especially where you maybe have difficult ground conditions, or we're sitting in a drill and blast environment. Then your hanging wall often has these undulations associated with it. Now, you can use your topographic surface that you derive from your LiDAR data to actually go and do topographic corrections to your GPR data. Here's just an example in the radar processing package. The radiogram on the left is not corrected for the topography. Your hanging wall surface is sitting here at time 0. So this is what it changes to if you apply that topographic correction. So you end up with a surface that mirrors the hanging wall topography, and you end up with a radiogram that is also now topographically correct according to that surface. And the idea is to integrate the two. You can drape your GPR outputs on that surface of the hanging wall where you did the survey. And ultimately, the plan is obviously to take this to the mine plan. So if you can do, whether you're just doing a few cross sections like we did here at Masebe, you can bring them into the mine plan software and overlay them in the actual mine plan. And you can obviously extend this to the 3D environment. Here's some examples of, well, this is one section, but here's an example of a complete 3D data cube draped onto the hanging wall surface. Here's just some other examples. Then moving on, I'm nearing the end now. This is just mentioning the application guidelines that were produced last year or the year before as part of the AOK projects. We had 2 separate projects, one focusing on the GPR research and one on the ERT. And for each of those, we produced a set of guidelines for industry use. And each of these guidelines basically covers all the important topics, from just giving a background about the technology. This is the one for GPR. Looking at how to plan and conduct GPR surveys, processing and interpreting your GPR data, looking at case studies. So while these application guidelines are not very detailed, it's not like a textbook with a lot of technical detail in it, but inexperienced users can take these guidelines and actually follow it step by step, and it will help them to plan and execute their own GPR surveys if they have a system on the mine. For the ERT, something very similar. Basically, it's just a separate guideline with this covering the same or similar topics. Okay, then looking at the way forward, there's a few topics that we feel should get some focus in the next few years, just to cement in a lot of these things that we covered in the past few years, and also going forward. I think training for mine personnel is a quite important thing. I know there are many mines, probably more than 24 mines out there in the Bushveld alone, that have their own GPR systems. It would be useful for those people on the ground to be able to execute GPR surveys effectively and know what to do with the data. Bringing in AI and machine learning, as I mentioned earlier, that I think is quite an important aspect going forward. And then the mounting of GPR on mobile mining machines or robotic platforms. Similarly for ERT, Training of personnel is important. I think we can put maybe a bit more effort into optimizing the survey logistics and methodology, although I think we've advanced quite a bit on that score. And then maybe looking at the 3D survey approach for ERT as well. It's not as straightforward as with GPR. You will probably need to exploit a lot more of your excavations around a specific area, but that's definitely something that we can look at. And then in closing, I just want to maybe put something on the table that will, there's no real answer to this, but just to sort of highlight where we are at the moment versus where we were maybe 20, 30 years ago. So back in the day, when you talked about in-mine geophysics, there was often a resistance to embracing new technology. Access to sites, and let's call it onboarding, as it's referred to these days, was relatively straightforward. It wasn't difficult to get to sites. Mobilization and data acquisition, that was a problem. Surveys were time-consuming and cumbersome. And also data processing and interpretation was slow, and a typical complaint was about slow turnaround times. So after all these research efforts that we put in the last 20, 30 years, how did that change things? We solved 3 of those problems, but the one that wasn't the problem 20, 30 years ago is potentially a problem now. I think we're seeing a general openness in the mining industry to investigate and implement new technology. However, it's quite difficult to gain access to sites and to actually prepare for surveys. Mobilization and data acquisition have improved quite a bit, and so has processing and interpretation. To the point where our turnaround times are now sort of more competitive and more attractive to the guys on the mine. I think that's the end of the presentation. Yeah, that's it. I don't know if there's opportunity for questions. Anybody wants to ask any questions? Yes, Susan.
Hi, Mike. Thanks for a great talk. Can you hear me okay?
Yes, I can.
Yeah. I wanted to ask, certainly in the early days, kind of the standard off-the-shelf radar just wasn't working very well underground. Have you found that it's more robust now, or are you still having to kind of toughen it up for the underground environment?
Susan, no, it's definitely improved. I remember when I first started in GPR, you had some systems that if you just knocked them too hard, the fiber connector or something broke, or the batteries died on you or something. There was a lot of problems with the systems early on. One of the other issues that I actually wanted to dwell on it a bit more in the talk today, but initially, I think the focus was a bit wrong. The people wanted to see as far as possible into the rock, so they tended to go for the low frequency systems that could see further. But they, in the process, compromised resolution, obviously. But more importantly, those low frequency systems were bulky, so the mines didn't like it if you pitched up with this huge box. So what we did in Platmine many years ago is we actually identified the niche applications for GPR, and we realized that it is really about hanging wall studies, immediate hanging wall, the first 3, 4, 5 meters of the hanging wall. And for that, you can use your middle frequency systems. And yeah, to actually answer your question, some of the systems that I've seen, including the ones that we use, they're commercially available, but a lot of the systems these days are quite robust.
Great, thank you.
Okay. Okay. Doesn't look like there are any more questions. Last chance. Okay, gone. Thanks, everyone. Thanks for the opportunity. Enjoy the rest of your day.
Thanks, Michael.